So for today, we'll be talking about chapter 3, the separation and purification technique. And in this case, right, when we take a look at this, these are the items that we need to know. Generally, it is actually cascaded based on the types of substance that we would like to separate from a mixture as well as from the different states. So when we take a look at, first of all, why do we want to do separation? Or is there a need to do it? So sometimes for substances, we are able to actually get a pure substance, where a pure substance is generally made up of a single one side. Is a pure substance is actually made up of one single element or compound, and it's not mixed with any other substance. So in the previous chapter for elements compound mixtures, we do realize that pure substances, they would generally have a fixed melting and boiling point, and therefore they have they are usually, if it's an element, they are usually made up of only that particular element. Okay, the other one is compound, but if it's compound, they must already have some chemical bonds attached to it to make it into a compound. So a mixture is generally made up of two or more substances that are not chemically combined together. So some examples of mixtures are like your orange juice, where you could see from the nutritional fact, it is made up of different items. For example, they may have carbohydrates, they may even have some of the compound of the orange in it. So together as a whole, they are then a mixture. When you look at air, air contains a lot of different other elements in it. You have your oxygen, you even have your carbon dioxide, which is actually a compound. You have a hydrogen gas and nitrogen gas. So all these together comes out with a mixture. Now, why do we not call air a compound? Is that all these elements, right, like oxygen, your hydrogen, they are not chemically combined together, and they exist as individual molecules or compounds. Therefore, you get a mixture of it. Then, how do we go about separating a solid from a liquid solution? Or generally, let's say I give you a sand and I put it in the water. How am I able to then get the sand out from the water? So that's what we are discussing about, getting the solid from the liquid. Here, we can actually do this process called filtration, where it is the process of separating an insoluble solid from a liquid. Now, the key thing here is insoluble. Insoluble means that it cannot be dissolved in water, okay, or basically in the solvent use. Um, so generally, how do we go about it? Because all these are insoluble, so they tend to be like particles and whatnot. And of course, the liquid portion will be just some solution. So what we'll do is we actually put this whole thing into a filter funnel, and the filter paper acts as the filter, okay, such that it is able to actually trap the substances if they are big enough and not small enough to be able to pass through the partially permeable side of the filter paper. So in this case, they actually they will stay onto the filter paper, whereas the rest will get channeled out of the filter paper, so they can pass through. So what we can see is that for the property or the principle behind filtration is that large insoluble solid particles are trapped by the filter paper in the funnel. And then these small particles are then able to pass through, for example, your liquid. So let's say for the filter paper, you have mini holes in it, okay, channels. Then of course within the solution form, you have all these particles. But of course you also have the equally small ones. Maybe put it in green. Yeah, that is small enough. So we have a lot of all this. So what we can see is that what will actually be filtered down is actually the small particles. Why only the small particles are able to move downwards is because they are small enough to actually filter it down. So let's say, imagine this particle, it is able to, let me try to get one. So we could see this small green color particle is small enough to be able to move around here, and when needed, it is able to pass through. So they actually got filtered down. Whereas if we look at the larger molecules, let's say this purple color substance, we could see that they get blocked because it's too large for it to pass through the partially permeable kind of filter paper. So upon filtration, what will the large particles be considered? It will actually remain on the filter paper, and generally we call it the residue. We do not call it the sand, we call it the residue. So the meaning of residue is like what is remaining. So we could say, so in this case, anything that gets not being able to filter down, we call it the residue. Whereas for the solution, they are small enough, and hence they are able to pass through the filter paper. That's why if the substance has undergone filtration, we call it the substance as a filtrate. Now, in this case, when it comes to the sand and the water, the sand is what we call the insoluble solid, and the water is actually the liquid part. So in this case, that's how they define it in the form of filtration. Next, we look at evaporation to dryness. So evaporation to dryness, right, is in a sense you want to obtain soluble solid from a solution. So soluble means it can be dissolved in water. So a main key difference between these two, right? For filtration, you are able to get both the solid as well as the liquid portion of it. Whereas for evaporation to dryness, what happens is when you have, let's say, the liquid portion as well as the solid items, that let's say it has already been dissolved in the water, right? I just draw for clarity, yeah. So the water will get evaporated. Are you able to obtain the water from the evaporation to dryness? The answer is no, because it's already trapped in the air. You will need to do another separation technique in order to obtain the liquid portion. So what is left on the evaporating dish is actually just the initial soluble solid. But because the soluble solid, right, you have the evaporation of dryness, you remove the water already, right? Therefore, what is left is just the solid itself. Okay, and in this case, when we use the example of salt from water, salt has a higher boiling point than water. Okay, so in this case, right, when you heat it up, the water in the solution is lost to the atmosphere, leaving the salt to be remain, because through the burning, the boiling point of salt hasn't been reached, so it will retain at the evaporating dish. Whereas for the liquid part, it has actually evaporated and therefore channeled into the environment. So not all substance can be obtained by evaporation to dryness. For example, your sugar, where sugar has a very low melting and boiling point. So what happens is this solid, right, obtained by evaporation to dryness is not always pure. And what will happen? The sugar will decompose upon heating. So any soluble impurities will also be left together with the solid after heating. Hence, you are not getting a pure solid. Instead, it's like something else altogether. With a combination of filtration and crystallization, with a combination of filtration as well as evaporation to dryness, comes the process crystallization, where in this case we are actually able to obtain soluble solid from its solution. One example is through hydrated copper 2 sulfate crystals. The meaning of hydrated means it contains water. While sodium carbonate crystals are just the compound itself. For the chemical symbol, it's Na2CO3. So next we look at how do we obtain pure copper 2 sulfate crystal. So most of the time, before that, we will prepare a saturated solution, and this one we'll learn more at a later chapter of salt. And what we'll do is we will actually heat most of it to remove most of the solvent water molecule. So this heating will prepare the solution to be even more saturated. Why is this important? This is important for crystallization to actually occur. For the impure copper 2 sulfate crystals, they will be obtained in they will actually be here. But after the the evaporation, the dryness of the water, you remove the water, the hot saturated solution will then slowly cool. That's after you have removed the heating element, which is maybe a Bunsen burner. So this solution that contains as much of the dissolved solute as it can at a given temperature, and that the dissolved copper-2 sulfate will slowly appear as pure crystals as it has heat, the crystallization point. And rapid cooling, when you let it cool at a very fast rate, will actually cause your crystals to be very, very small. However, if you cool it slowly, over a long period of time, it will produce larger crystals or larger copper-2 crystals, sulfate crystals. After you obtain all this, you want to remove the remaining crystals through filtration, where the residues is actually washed with cold distilled water. Now, over here, you wouldn't want to actually use a lot of water because that will actually cause the copper-2 sulfate to actually be, dissolved again, as some of them are actually soluble in water. So this is something that we tend not to do that much. It really depends on whether the salt is soluble or insoluble. And finally, after what we do is we will tend to dry it between filter paper so as to remove any excess water. We would also be very mindful with not overheating it because sometimes if you overheat it, it loses too much of water crystallization. The copper-2 sulfate can actually undergo decomposition. It will turn rather than blue, it will turn white. Next, we look into separation of solid. So when you want to separate solid from solid, right, you must first assess whether both solids are soluble or insoluble in water. So to separate a mixture of two solids, we use a solvent in which one of the solid is actually soluble, while the other one is definitely insoluble in that specific solvent. Why did we use the word solvent rather than we use the word water? It's because another kind of solvent is maybe oil, and water and oil are two very different things. So different solids are able to dissolve in different solvents, and some of the common ones are like your water and ethanol. Ethanol is an example of an oil kind of solvent. So let's say you have sodium chloride and salt. So sodium chloride, right, in the layman's term, is actually a common household salt. And what we know is that salt can dissolve in water. Okay, common salt can dissolve in water. Whereas for sand, no matter how much water you add, it's actually silicon dioxide. The sand will not be able to be dissolved in water. So if you have these two, how are you able to separate it rather than as compared to you physically pick each of them? Some sand maybe is white color, so it's harder to separate. So what you do is, first of all, through that mixture, you add water to dissolve the sodium chloride first. When you dissolve the sodium chloride, you will form a sodium chloride solution and sand. So imagine it as a liquid portion, and some of it is actually your sand particles that cannot be dissolved in water. So next, what you do is you filter it. By filtering this sodium chloride solution, and then of course you have the sand. The sand will get filtered to form your residue, whereas your sodium chloride solution becomes your filtrate. So what will happen is, when it comes to of course you may have some traces of sodium chloride solution. What you do is, because sand is insoluble in water, you just add more water to dissolve it. Okay, the other one is the filtrate, right, which is the sodium chloride solution. What you can do is you collect it, and then in order to re-get the sodium chloride solution in a solid form, you evaporate to dryness. So the main key difference here is you want to get it into the solid form. So you just remove the water. Then of course, adding distilled water just to remove any traces of impurities of sodium chloride, and then you will be able to obtain already. Sublimation is used to separate a solid that sublimes from one that does not, and some substance such as your ammonium chloride and iodine sublimes. Sublimes is basically meaning, right, this method where first of all you separate the substance that from one that does not actually sublime from each other, such that you are separating a solid that can actually form a vapor very easily, like a liquid solid form very easily. So one way is like maybe your mixture of iodine and sand. Why iodine? Because iodine has a lower boiling point or melting point. actually more of a boiling point than sand. So when you heat it, right, the iodine becomes the gas very easily. And what we have is a wet cloth to cool it. So in a way, you try to condense the iodine vapor and then slowly, not just condense, but sometimes to even cool it further to form solid, and then it will all stay near the funnel. Usually, this process we tend to actually your melting point and boiling point of the substance tend to be very close to each other. That's why you are able to see this transition where they usually skip the liquid part. Next, when we look at magnet, right, a magnet tends to be able to separate a magnetic substance from a non-magnetic substance. The key thing here when we talk about magnetic substance is that a material that can be attracted to magnet itself can be a magnet, itself can also not be a magnet. That's the meaning of magnetic substance. So you can say a magnet or can attract, can be attracted by a magnet. Okay, so some examples of magnetic materials are like iron, steel, nickel, and cobalt. So when we use we can use a magnet to separate two solid. Like for example, we have sand and maybe iron steel nails. So how are we able to get the iron steel nails? We just put a magnet because iron is actually a good magnetic material that can be attracted by the magnet. It can also be the iron nails is a magnet itself, and it's easier to separate itself. So next we look into separating a liquid from a solution. So before we go into this segment, I think we will pause here for a while, take the time to recap what we have gone through, and then we'll continue in the next video. Thank you.